So today I have one more video for the learners, people who want to learn AI more than just the surface and the tools and the usage that I sometimes cover in my videos. The reason I'm doing this again, because the last time I did that, which was the only time, I actually took a bet on creating such a video. So I thought to myself, I'm gonna dig deep in the transformer architecture, cover the papers around it, cover the concepts behind it, and see how it goes. It was a 2.5 hour video that I bet my wife, I told her, I did it anyways, I don't think even 10 people will watch it. I was so wrong. So the whole community and people beyond the community proved me so wrong. It was one of the best performing videos, at least for my scale. It got so far 3,200 views of people who actually clicked on a video that is 2.5 hours long. Even I sometimes don't do that unless I'm really interested in the topic. So it's doing well, and I got lots of comments around people are interested actually to have more of that. They want to learn these concepts. So when I've done the transformer video, I've actually did it as I learn on the go while doing some homework ahead of it, but actually reading and learning on the video with you and getting these concepts together. And it helped me personally, and clearly it helped some people from the feedback I received. So this is one more video, which probably will be on the longer side. So looking at all of that interest in the transformer architecture video, I thought to myself, this could be something that actually the audience, the community I have wants, and other people might actually be interested in. So we've covered that video. We've covered the transformer architecture. And I can tell you, based on the further reading I've done just to prepare for this one, if you did that, you already know 75% of what is there to know even till date from 2017. It is that significant as a paper when it came out that till today, at least from what I see, what I read, the most things we see around us when it comes to AI are highly influenced still by the same fundamental architecture that we looked at. So I decided, okay, we have the architecture done. It's there for people who want to watch it later on. Now I'm gonna do something that will bridge what happened in 2017 with the transformer architecture and until 2024. So I want to cover around 6 or 7 papers that are so significant during that time that brought us to 2024. So we'll look at all of that. Maybe we'll spend a long video. Hopefully it will be not as long as the first one, because the transformer architecture, as I said, is 70% of understanding the whole way, at least for the technology we see it today. And beyond that, actually, as things come in, there are many things that I can cover in the future, I know, but I don't want to keep doing these long videos for your sake. So today, another one may be long, but what I will do, I will take what you know already from the transformer architecture video, and I will take you with me until 2024. Beyond that, if this works, if people are still wanting to see such content, we'll start going into papers that we do through shorter videos, but we go deeply into those concepts and we try to understand them. And it will be a new mission, part of this channel, not only to get you to do automations, build systems, and empower your life with AI, actually get you to really understand AI. And by the way, just by doing the transformer architecture video, that would put you, in my opinion, at the 1% of people globally that understand AI. And as we keep doing that, probably we're going to be part of that really small percentage of people who have the time or invest the time to really understand the technology that we're using every day. It's fine to use these tools. It's great to use these tools. But I think any of us who want to go somewhere when it comes to this technology, do something with it at some point, it will always come in handy that you really understand what you're dealing with. So without wasting any more time, let's jump right in. And hey, subscribe if you're new to the channel. It's free.
Subscribe to Daddy's channel. The mic.
Before jumping into the real fun stuff, I just wanted to highlight something. In that video around the transformer architecture, I hit a small nugget. So I said, whoever actually watches the whole video, which I didn't expect at all, from start to finish, please, at a certain point, I mentioned at the end, please put a comment so for me to know that you actually did the whole thing. And I have at least one person I know of who did that, so I'll highlight that person. Others, and it's totally understandable, probably skipped through the important parts, maybe didn't go over me repeating over and over certain concepts, which is fine as well. Thank you for watching. So I promised something, I have to deliver on it. So you see the video and you can see the chart here, by the way, just compared to my usual performance. So that was something that I never expected. Okay, so if you go to the comments, so I have one great person here who simply wrote me this. I'm that one person, I guess, to watch from end to end. Here's a comment. So a shout out, and I'm sorry if I butcher the username, Yukuta Finney. So I don't know who's the actual person behind it. Thank you very much. You know, I really appreciate it. I wouldn't have expected anyone to do that. I hope I gave you value. And for the others who took the time to comment and interact with me and tell me this is something they want, this is something they appreciate, thank you very much for entrusting me with your time and watching the video even at parts. And it's always there. If you didn't continue it, you can go always back to it. Now, let's go and see what happened since the transformer architecture, at least the main big things, and until 2024. There are many papers that come out weekly. We're not talking about a paper in a year. It's not how this kind of industry is working. This is moving like light speed. So many people are working towards it, which is great. So you can see lots of papers coming every day. So usually on weekly basis, depending on the week, it could go to 50 papers per week on so many topics around AI. So what I try to do based on my knowledge, my understanding and the research, to look at those pivotal papers, pivotal changes that happened between 2017, since we got the transformer architecture, until 2024. I am sure there are many other important papers that I have missed, but for me, I wanted just to give you the big ideas that as we go in 24 and even further, as we get new papers, new open source models coming in, we study them, we have those kind of pivotal concepts understood, or we're aware of them, so we can continue down that path of understanding AI as it grows and develops and is reshaped and reshaping our lives. So let's start digging now. So I will start with the transformer architecture, and I will not spend a ton of time on this. I just want to refresh everyone on it so we can go and look at the newer stuff. But basically we looked at the input embeddings. How does embedding work? What is it exactly? We looked at positional encoding, how those go into matrices of numbers based on the embedding, and how it goes to the multi-head attention, which is comprised of single product attention. And this is where the magic happens. So the model here can actually understand the relationship between words and assign those kind of attention where it should pay attention in terms of one word to the other words in a sequence. And we go through the feed forward network and then add and normalize. And then we go to the encoder decoder on the output side. And we looked at the masked multi-head attention and why it is masked. And then the same goes in. We looked at all the phases and the manipulations that happen. I used to call them manipulation in that video, but basically it's all mathematical equations as part of the single product attention and the multi-head attentions that take us eventually to roll back from numbers into words, and we start predicting the probability of the next token and the next token and the next token, looking at the whole context of the input and the output being generated and how that goes into sequence. So I hope this will refresh your mind. And even I kept at the end of that video, and you can find it in the description, some tools that visualize how this thing works in terms of probability that we get at the end, which will decide which word will come in as the next token in the output. So just a refresher, keep that in mind. This is big part of what we will cover as we go forward. Now, before jumping to the first paper, I want just to establish an understanding of a concept that will come in handy as we progress in the papers. So that concept is the model pre-training. So what is a model pre-training? So let's just read through this paragraph and then we'll move forward. Let me make it bigger for a second here. Okay, what is pre-training of language models? Pre-training is a technique used in natural language processing to train a language model on a large amount of unlabeled text data before fine-tuning it on a specific task. The goal of pre-training is to create a model that can learn the structure and patterns of language, allowing it to develop a deep understanding of the language and generate coherent and contextually relevant responses. Fine-tuning a pre-trained language model involves training the model on a smaller labeled dataset specific to the task, such as sentiment analysis, text classification, or named entity recognition. The pre-trained model is then adapted to the specific task, resulting in improvement performance on that task. For example, a pre-trained model might be fine-tuned on a sentiment analysis task to classify movie reviews as positive or negative. Several pre-trained language models have shown significant improvements when fine-tuned on a specific task. BERT, which is the bidirectional encoder representation from transformers. I will stop here because we'll go deeper into this in the actual first paper that we cover, but I want you to understand that there's an idea that came at some point, which we'll see now, where rather than training models for tasks, someone actually questioned the logic in doing it this way, and people came up with the idea that why don't we just give it unlabeled data, try to train the model or pre-train the model on language in general, and then fine-tune it to tasks. Now, I've covered some videos in the past where we fine-tune, for example, the 4O model to do something specific. It is somehow similar to this. So I train the model to understand language, and then I fine-tune it to understand certain specific use cases, because just by the pre-training itself, it doesn't perform as well across all of these tasks. So rather than doing, let's say, a model that does translation or sentiment analysis and repeating all of these things, I would actually do it differently. This is the idea, not my idea, is I pre-train the model to understand language in general, and then I fine-tune for translation, I fine-tune for sentiment analysis, I fine-tune to whatever case I have. Just an idea to keep in mind. And with this, let's go to the actual paper that they wanted to continue talking about here that brought this idea to everyone. Okay, so here we start with the first one, and this is where I actually stopped reading into the pre-training and fine-tuning concept, because this came from Google. So we all know BERT, the name BERT. It was the first name Google gave to their AI. Later on, they dropped it. They moved to Gemini. And this is the paper, and just to keep the timeline in mind, which is Transformer Architecture came in 2017. BERT, this paper came in 2019, May of 19, as you see here. So BERT, this is the title of the paper, BERT Pre-Training of Deep Bidirectional Transformers for Language Understanding. We'll go through it and we'll understand what Google did in 2019 that was different from the transformer architecture, and why actually they called it BERT as a model. I don't know why they named it later on Gemini, but maybe it's a marketing thing. But we'll at least here we know why they called it BERT. So let's start with the abstract. Not all the papers I will show you are highlighted, color highlighted. The app works, the highlighting app works sometimes it doesn't work. Hopefully this will not be a big problem for you, but every text I'm reading, it's in front of you. So let's read the abstract. This will just bring us into the paper that they created, and so for us to understand what they're trying to convey in terms of a challenge. Usually these papers have a problem and a solution. So let's start with the abstract. We introduce a new language representation model called BERT, which stands for Bidirectional Encoder Representations from Transformers. Unlike recent language representation models, BERT is designed to pre-train deep bidirectional representation from unlabeled text by jointly conditioning on both left and right context in all layers. As a result, the pre-trained BERT model can be fine-tuned with just one additional output layer to create state-of-the-art models for a wide range of tasks, such as question answering and language inference, without substantial task-specific architecture modification. BERT is conceptually simple and empirically powerful. It obtains new state-of-the-art results on 11 natural language processing tasks, including pushing the GLUE score. So these are benchmarks. We will see them everywhere when it comes to AI models. There are benchmarks these kind of AI companies or AI models use to really track the performance improvements and compare model to model and even their own model as it is improved. So this just here, the last part shows you the improvements the BERT model at that time when they tested it actually showed them. This is why I covered the pre-training and fine-tuning before. So fundamentally what they've done, they say, we found that it's much better to actually pre-train the model on language, unlabeled data basically. It makes the training process easier. And later on, we go and do fine-tuning per task. We did it over 11 tasks, and that gave us like a state-of-the-art model. So I would assume that it just made the process of putting the training data together, preparing the whole cooking process for the AI model fundamentally much easier. And I think this saved them a lot on the computational requirements for training these models. So rather than training every task, as we said, we pre-train a model and then we fine-tune it. And they said it's through a single layer of fine-tuning, you can get really high-performing models. So let's carry on with this and see what they're bringing to us exactly when they talk about all of these concepts of bidirectional, which is something unique we didn't really read into yet. So I will carry on into the introduction. Again, that early part usually is very solid, very strong. When reading any paper, I recommend you to always read that part. Okay, language model pre-training has been shown to be effective for improving many natural language processing tasks. So again, the same thing. These include sentence level tasks such as natural language inference and paraphrasing. So these are some of the tasks they say it works well with, which aim to predict the relationship between sentences by analyzing them holistically, as well as token level tasks such as named entity recognition and question answering, where models are required to produce fine-grained output at the token level. Again, all of these links that you see here always refer to certain studies or papers that came out in the past related to this area they're talking about. I checked them out, and again, I'm only covering what is really significant for us to know what happened from 2017 to 2024. Okay, so let's carry on back to the top. There are two existing strategies for applying pre-trained language representation to downstream tasks: feature-based and fine-tuning. The feature-based approach, such as LLaMA, again, this is a paper where it refers to this kind of methodology, uses task-specific architectures that include the pre-trained representation as additional features. The fine-tuning approach, such as the generative pre-trained transformer, OpenAI GPT basically, which is here they're referring to a version in 2018, I think this is maybe GPT-4, introduces minimal task-specific parameters and is trained on the downstream tasks by simple fine-tuning all pre-trained parameters. The two approaches share the same objective function during pre-training, where they use unidirectional language models to learn general language representations. Now, okay, so it's just saying what used to happen before, and now probably they're going to say what they did differently. So they say there's two ways of doing this. One of them is what we talked about, which is the fine-tuning. They said all of them have the same goal of modifying the model to a certain task for a certain performance. And they talked about OpenAI's GPTs in concept and how that works. And they're highlighting all of them are unidirectional. And now I think they're going to talk a little bit about what they mean when they say bidirectional models. So let's read through and see what we learn from this part. We argue that current techniques restrict the power of the pre-trained representation. And again, before I continue, if you remember when we were reading, they talk about how the pre-trained model is used as part of the parameter in the fine-tuning. So this is, I think it will be an important piece of information before we go to their own argument. So we argue that current techniques restrict the power of the pre-trained representations, especially for the fine-tuning approaches. The major limitation is that standard language models are unidirectional. So here they're hitting on that kind of limitation. And this limits the choice of architectures that can be used during pre-training. For example, in OpenAI GPT, the authors use a left-to-right architecture where every token can only attend to the previous tokens in self-attention layers of the transformer. Again, this link, this is the attention is all you need paper. So you see how it is significant. You'll find it probably in any paper for the following 6 years from the day it went out. Such restrictions are suboptimal for sentence level tasks and could be very harmful when applying fine-tuning based approaches to token level tasks such as question answering, where it is crucial to incorporate context from both directions. So just to take a pause here, what they're saying is the way the transformer architecture at least is being deployed. And if you remember, when we looked at the transformer architecture, we looked at how the input comes into the encoder and then how it goes through the encoder-decoder step on the right, and how always the actual encoder-decoder, the multi-head attention is masked. So it will only see the next word. So it's looking at like right to left. So we have the input, and then we have each word or token being predicted from that architecture, and it's masked, so it doesn't see the other potential words coming on the right of the current word or token being predicted. So what they're saying here, that this could be harmful, and that basically potential is lost of looking at the context of the attention towards what's there on the left of it and the right of it. And we're talking, when I refer to it, it's the, I assume, the word being predicted or the token being attended to when it comes to attention and probability of what should come in. So they're saying we need to look at the left, we need to look at the right, and that is what they call bidirectional, because everything ahead of this paper was unidirectional, just looking right to left or left to right. So let's carry on. Maybe we'll get more understanding around this. In this paper, we improve the fine-tuning based approach by proposing BERT, bidirectional encoder representation from transformers. BERT alleviates the previously mentioned unidirectional constraint by using masked language model. So this is what they're proposing apparently. LLaMA, pre-training objective. The masked language model randomly masks some of the tokens from the input, and the objective is to predict the original vocabulary ID of the masked word based only on its context. Unlike left-to-right language model pre-training, the LLaMA, which is the masked language model, objective enables the representation to fuse the left and the right context, which allows us to pre-train a deep bidirectional transformer. In addition to the masked language model, we also use a next sentence prediction task that jointly pre-trains text pair representations. The contributions of our paper are as follows. So let's read that, it's important. But again, we get the premise here. They want to go basically bidirectional rather than unidirectional. They're replacing the masking. I assume I understand it correctly. They're replacing the concept of masking, but what they call masking language models, where they randomly mask tokens from the input, and maybe we'll understand a little bit of how that works. So let's just go into the contributions they think this paper will make in terms of this change when it comes to how you handle these kind of pre-training and fine-tuning of language models. We demonstrate the importance of bidirectional pre-training for language representations. Unlike, again referring to a paper, which uses unidirectional language models for pre-training, BERT uses masked language models to enable pre-trained deep bidirectional representations. This is also in contrast, again, to the paper here, which uses a shallow concatenation of independently trained left to right and right to left language models. So again, it all revolves around how these previous versions were just looking at a single direction at each time, and that could be right to left and left to right. I'm not exactly sure what they mean when it's left to right and right to left. You can go into that paper that they're referring to here just by copying the name and searching for it. You'll get usually the PDF from the first search. But the idea that is important here, that now we are going bidirectional rather than unidirectional. So let's go for the second one. we show that pre-trained representations reduce the need for many heavily engineered task-specific architectures. BERT is the first fine-tuning based representation model that achieves state-of-the-art performance on a large suite of sentence-level and token-level tasks, outperforming many task-specific architectures. Once we had the transformer architecture, usually people went and did task-specific models trained for that specific task of, let's say, question answer or translation or whatever. What they're doing here, they came in and said, rather than doing all of these separate specific task model trainings, what we are going to do is we are going to actually have a generic pre-training of the language model, unlabeled data, and then we're going to take that and fine-tune it. And rather than doing this in a unidirectional manner, basically looking left to right or right to left, whatever that means, we're going to do it bidirectional. So this is like a tweak to how the basic transformer architecture works. So let's carry on. Maybe that will clear the understanding for us as we read more through this one. So here they end with this third point of BERT advances the state of the art for 11 NLP tasks, natural language processing tasks. The code for the pre-trained models are available. Again, this is the GitHub for the pre-trained model, so you can go and play with it if you want, if this is your thing. Now, let's carry on reading. Maybe we'll just get these concepts more and more into our understanding. At some point, I'm going to stop where I think beyond that, it will be all about the testing and other details of the paper. I just want to really touch on all the concepts they're bringing forward in this paper. Okay, so let's come to this. Again, I think these kind of visuals usually just gets things to start connecting in your head. So this is the pre-training. So you have the masked sentence A, masked sentence B, and again, their masked language model kind of methodology does random masking of the input as they mentioned. So you have the masking here. You have the already things are tokenized, so you can see all of them are in tokens. You have the CLS. If you remember when we did the transformer architecture, there are special tokens they call that tell the model this is the first token or the last token, something like that. And I assume this is the feed forward type of network here. And okay, you have the data points or embedding. These are the inputs. These are the outputs of the feed forward, I assume. And then you have the masked language model. So we do the pre-training. The output of it is the masked language model, what they call. It's basically the pre-trained language model. Once we have that, and what they said is through a single layer, I assume, you do the fine-tuning. So you create that pre-trained model using unlabeled data, and then you start just fine-tuning per task through a single layer. Again, if I understood correctly. So here you see question and paragraph. So this I think this is like the task of squad is the question answer probably. And again, you go through the tokenization and you go to, I would assume, a single layer of just fine tuning it, and you get the output, which is start and span. I assume that's the output with the weights, with everything of that fine-tuned model. So let's read just what figure 1 actually has as a description. Overall, pre-training and fine-tuning procedures for BERT. Apart from output layers, the same architectures are used in both pre-training and fine-tuning. So it's the same architecture. The same pre-trained model parameters are used to initialize models for different downstream tasks. During fine-tuning, all parameters are fine-tuned. CLS, okay, is a special symbol added in the front of every input example. And SEP, I don't know where we see SEP here in the middle, is a special separator token. Example, separating question and answer. So again, part of these special characters. So they're just giving some kind of description and legend for some of these tokens there. I think it's more important just to understand what happened as a difference from the transformer architecture. So we got an architecture that actually you train the whole model on labeled data, on tasks, you run it through that model, and then you can actually use it in predicting the next token. This is different. Like this is, so there was a jump in that technology somehow, where they said, rather than doing that task-wise and going through all of that headache, it doesn't make sense that when we talk about language, still models using the transformer architecture are not really handling language as natural language processing on the ground, like on application. So they said we should give it unlabeled data, unlabeled language, and I assume that made the process of pre-training these models much easier, at least for the people preparing them. So they just basically, I assume and I understand correctly, they give it lots of text, go understand the language in general. After I have that model developed, it's not perfect, probably if you interact with it at that phase, it might get lots of errors. What they did after that is they said, okay, now I'm gonna fine tune. This is what I'm doing differently. I will fine tune per task based on that model, and I get the final product based on that fine tuning only, and the MLM, the general MLM, and the specific fine tuning, and that's how I do it. And also you can see here they're talking about context in the terms of sentences and paragraphs. So also that was a change from the transformer architecture in terms of predicting the next token, and they're doing it more on the fine tuning. But again, all of this, like, you know, if we continue reading, I'm not sure, we'll see, and we go under the hood, you're going to find that all of this is influenced maybe 90% by the same transformer architecture behind all of these calculations. So it's not that they're bringing a new technology when it comes to the actual training of that model and the prediction, the inference of that model. It's just they're changing a little bit maybe the architecture. I don't know if that's a good depiction, but the logic, the usage, basically the flow of how they do things is what they're significantly changing. So let's continue reading for a little bit just to make sure we got everything right when it comes to BERT, and then we'll move to the next significant paper that we got between 17 and 24. Okay, let's go to BERT. Now they're again focusing on the model itself. We introduce BERT and its detailed implementation in this section. There are two steps in our framework: pre-training and fine-tuning. Okay, we got that. During pre-training, the model is trained on unlabeled data over different pre-training tasks. For fine-tuning, the BERT model is first initialized with the pre-trained parameters, and all of the parameters are fine-tuned using labeled data from the downstream tasks. Okay, so what they're saying is they do the pre-training, they use specific parameters for that, and in the fine-tuning, they just modify these, which is the word fine-tuning. So they modify the same parameters from pre-training to really get it to operate within a certain task. Okay, makes sense as we read it. So let's continue. Each downstream task has separate fine-tuned models, even though they are initialized with the same pre-trained parameter. So we have to think about each task having a different model. Each of them is different. The question answering example in figure 1 will serve as a running example for this section. Okay, they're going to use question and answer as an example. A distinctive feature of BERT is its unified architecture across different tasks. There is, continue, minimal difference between the pre-trained architecture and final downstream architecture. Okay, makes sense as well. So they're not switching the architecture a lot. Model architecture. BERT's model architecture is a multi-layer bidirectional transformer encoder based on the original implementation described in... Okay, this is what you see here. This is the paper we covered in the transformer architecture. This is the original transformer architecture. And they are telling us that the BERT model architecture is a multi-layer bidirectional transformer encoder based on the original implementation. So probably if they show the actual architecture, it will look exactly like the transformer architecture. So this is what was important. Maybe they're using it differently, but the architecture is the same. Because the use of transformers has become common in our implementation, is almost identical to the original. So they're saying it's almost identical to the original architecture. We will omit an exhaustive background description of the model architecture and refer readers again to the same paper which is Attention is All You Need, as well as excellent guides as the annotated transformer. Okay, so it's nearly the same as the original transformer architecture, and they're just highlighting to the same paper. Attention is all you need, and other references for people to read. In this work, we denote the number of layers, transformer blocks as L. Okay, so this is like the detailed things. If you want to look into the calculation of BERT, you probably can it's important to understand these parameters, how many layers, etc., 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 what each variable means. So let's carry on. I think total parameters, by the way, for this model was 340 million parameters. I know today, if you look at what we have, this is nothing. Like this was like literally a drop in a bucket compared to the models we have today. BERT base, okay, was chosen to have the same model size as OpenAI GPT. So they have a base model, which is this one, which has 110 million parameter, and that is equal apparently at the time to OpenAI GPT. I think here when they talk OpenAI GPT, that's GPT-2. Not 3 definitely. For comparison purposes, okay, so they created BERT base to compare it to OpenAI GPT to have that benchmark. However, the BERT transformer uses bidirectionally self-attention, while GPT transformers uses constrained self-attention, where every token can only attend to context to itself, which is the transformer architecture. Again, these are the smaller parts that either I misunderstand or they're just beating on OpenAI. But I think here what they're saying, oh, we're different because we have that bidirectional kind of context for the input and output, while the transformer architecture used like the basic one that OpenAI ChatGPT at that time were using is simply looking at the self-attention part of things rather than wider bidirectional attention. So input-output representation. Okay, so I will keep reading. I think I just looked ahead. I think we have 2 more pages that definitely will give us everything we need to know of what happened when BERT came out first during 2019, and how that was significant and how that model operated compared to what we had before. And then we can move forward. Everything else, I just scrolled through this before I continue, are things around how they tested, what the results they got, how they put that together. Just things I don't think for our video is interesting, but I think the next section is really interesting in the sense we're gonna detail certain aspects that they talked about in the introduction and the pre-work first. We're going to read more into those concepts that will actually get to understand them. So I was a little bit having that gray kind of understanding so far. I think this will make us more closer to having like a robust understanding of what BERT brought and how it works. So again, input-output representations. To make BERT handle a variety of downstream tasks, our input representation is able to unambiguously represent both a single sentence and a pair of sentences, so a question and answer. So they said at the beginning they're gonna, for the whole paper, they're gonna focus on one task just to showcase, which is the question answer in one token sequence. Okay, throughout this work, a sentence can be an arbitrary span of continuous text rather than an actual linguistic sentence. A sequence refers to the input token sequence to BERT, which may be a single sentence or 2 sentences packed together. Okay, we use word piece embeddings. So this is a specific embedding which has 30,000 token vocabulary. The first, again, if you don't understand why they say token vocabulary, go to the first video. It will talk about embedding, or just look it up what embeddings are actually. The first token is in every sequence is always a special classification token, CLS. So we talked about that before in the previous video as well. The final hidden state corresponding to this token is used as an aggregate sequence representation of classification tasks. Sentence pairs are packed together into a single sequence. We differentiate the sentences in 2 ways. First, we separate them with a special token, SEP. Second, we add a learned embedding to every token, indicating whether it belongs to a sentence A or a sentence B, as shown in figure 1. And we denote input embeddings as E, and the final hidden vector of the special token as, okay, some of the equations here, the final hidden vector. Okay, so basically they're saying they're pushing sentences when they did the answer question. they separate them, and the sentence doesn't necessarily have to be something linguistically we understand, so it doesn't make sense necessarily. There's a question and an answer. They put them together. It could be like one sentence or two sentences. There's always a token to tell the model this is the start. Also, they use a token that sometimes comes in the middle, so it splits the input from the question from the answer. Or they have certain tokens that tell the model this is sentence A and sentence B. So this is just a paragraph about some of the techniques they were using just to prepare things and develop and train the model. So let's go to pre-training BERT. I think this is where things get really interesting for us. So unlike, again, this is the same paper they were referring to before, we do not use traditional left to right or right to left language models or to pre-train BERT. Okay, instead we pre-train BERT using two unsupervised tasks described in this section. So there's two tasks to pre-train the model. This step is represented in the left part of figure 1. So the figure 1 is the figure that we looked at. So the left part which talked about pre-training, we can go quickly back to that. So we're going to now look at this, and I assume later on we're going to look at this. So just keep this in mind. You can open the paper and just look at it while you listen to me if you want. Hope that helps. I'll read it for you. Okay, so intuitively, so this is the first one, masked language model. So this is the LLaMA they were talking about. Intuitively, it is reasonable to believe that a deep bidirectional model is strictly more powerful than either a left-to-right model or the shallow concatenation of a left-to-right and a right-to-left model. So I think the concatenation of a left-to-right and right-to-left is this paper they're referring to. It was talking about that methodology. Unfortunately, standard conditional language models can only be trained left to right or right to left, since bidirectional conditioning would allow each word to indirectly see itself, and the model could trivially predict the target word in a multi-layered context. I hope I understood something here. So let's continue reading on, maybe we get the idea. In order to train a deep bidirectional representation, we simply mask some percentage of the input tokens at random. So they do random masking, not just masking as the original transformer, and then predict those masked tokens. So they mask randomly some tokens and they predict them. Okay, let's try to understand why that makes sense or why that's important. We refer to this procedure as a masked language model, so the LLaMA again. Although it is often referred to as a closed tasks in the literature, so this is the paper that they talk about here. In this case, the final hidden vectors corresponding to the masked tokens are fed into an output softmax over the vocabulary as in a standard language model. In all of our experiments, we mask 15% of the word piece tokens in each sequence at random. So if you remember, the word piece is the embedding that has, I think, 30,000 dictionary, 30,000 token dictionary. Okay, so they mask 15% of all of them in random. In contrast to denoising autoencoders, we only predict the masked word rather than reconstructing the entire input. Okay, I'll just carry on and try to make an understanding out of this. Although this allows us to obtain a bidirectional pre-trained model, a downside is that we are creating a mismatch between pre-training and fine-tuning, since the mask tokens does not appear during the fine-tuning. To mitigate this, we do not always replace masked words with the actual mask token. The training data generator chooses 15% of the token positions at random for prediction. If the ith token is chosen, we replace the ith token with 1, the mask token 80% of the time, and a random token 10% of the time, or 3, the unchanged ith token 10% of the time. Then Ti, okay, this is just part of the equations, will be used to predict the original token with cross entropy loss. We compare the variations of this procedure in Appendix C2. Okay, so reading all of that, I read it again offline just to try to put the understanding. But the way I understand it is for them to be able to do the LLaMA, which is the masked language model, to achieve that kind of bidirectional requirement, what they do is they get the input. So remember, they mentioned clearly that we are dealing with unlabeled language. So let's say you get an input, a sentence. So let's say, for example, a sentence like, the boy went to school, okay? And what they do with that input, as they mentioned here closer to the end, is that they always mask 15% of the input tokens. And they do it randomly. So let's say the boy went to the school. So it could be at one time they mask the word boy or the word school. And in pre-training, what they try to do is predict that masked word. So let's say, which is 15%, but here, just to make it simple, we're deciding it is one word that they're masking. So if they mask boy, the model will try to predict what is the word. So it might come up with the man went to school, not the boy went to school. Or if they mask school, it can be the boy went to, it might predict park, it might predict school. So this is one aspect of it. And what they're saying, it's not always like that. So 50% of the time they're doing this masking. And then there's 10% of the time they're fundamentally actually assigning a random word on top or to replace that would have been masked token. And there's 10% of the time that they basically don't touch it. Keep it as it is. So this is at least what I understand from reading this. So let's continue. So now at least we understand how it goes into training. Before, what we understood in the transformer architecture is that we get the input and then we try to predict the next word. Here it's different. We get the input, we try to actually mask a word in the input and predict a word. Again, this is the pre-training, so we're not getting the output, but just that's the different part. We're trying to predict a masked word in the input at times, 15% of the time, and it happens through different ways. So not always it's a masked word that we're trying to predict in that input. Sometimes it's just throwing in a random word. I don't know, I didn't understand why is that. And then sometimes it is just keeping it as it is, as the input. So let's carry on reading. Maybe we'll get the full picture as we continue reading, but at least I think I understand how the first part of the pre-training is happening. I would simplify it in saying we mask a random word from the input. 15% is what they're looking for. We try to predict that word, basically. So we know the input. We know this word, what actually it should be. We mask it. We get the model to predict it, and we see what we get on the other side. This way, the training process, or the pre-training process to be more accurate, we can tell, are we getting it right or not? And does it need to go into more sequences to actually get it right? So that makes sense at that simple level for me reading all of that. Let's carry on with the second task here. So task 2 is the next sentence prediction. So, okay, we're testing it in predicting a word within the input. And this is linked to the attention, the way attention works. Now, the second task is we want to get it to predict the next sentence. So let's read about that a little bit. Many important downstream tasks such as question answering, QA, and natural language inference, NLI, are based on understanding the relationship between two sentences, which is not directly captured by language modeling. Okay. In order to train a model that understands sentence relationships, we pre-train for a binarized next sentence prediction task that can be trivially generated from any monolingual corpus. I think monolingual corpus is just like a body of words, a body of language. Specifically, when choosing the sentence A and B for each pre-training example, 50% of the time, B is the actual next sentence and follows A, labeled as is next, and 50% of the time, it is a random sentence from the corpus labeled by not next. Okay, that's interesting. As we show in figure 1, C is used for the next sentence prediction. Okay, and speed. Despite its simplicity, we demonstrate in section 5.1 that pre-training towards this task is very beneficial to both Q&A and NLI. So these are like related to two specific tasks. We can go back now to the diagram and just give it a final look. What I understand is then when they try to predict the next, so okay, we cover the first part, right? The task that task is done. Now they're trying to predict the next sentence within the training model, and they're using again these standard bodies of language, which have like standard sentences they can use, and they link them with each other. So we start with a sentence, and then there's some kind of labeling they're talking about here. It's either is next or not next. And I think this just gives the model a clue if it's predicting in the right manner or not. And 50% of the time we have is next, and 50% of the time. So it's like a toss of a coin, I would assume. And I think this is, they're saying it's simple, but it's very, very efficient in pre-training the model. Okay, let me go back to the diagram. I will not go forward, because later on they speak more details around how they fine-tune it and how all of that works, more details and numbers and results. You can do that on your own pace, but I think we get the difference now of how they use the transformer architecture in a sense differently. We're not predicting following word, we're actually doing it in two ways to train this, the general training of the language model before the fine-tuning, which is the same architecture. We predict one word of the input that gets masked, we try to predict it. We definitely know it because we have it as part of that corpus of language. We're pushing in, we mask one word, and then we tell the model, predict this word for me, and we get a prediction. This is one part of it. The second part is we tell it, this is the sentence now, predict the next one. And we have some kind of labels which is next, not next. So we can tell, okay, this is what it predicted. The model itself, as it trains, it can tell, okay, it was the right prediction or the wrong prediction from that sentence input. So we can have that basically link between what it gets and what it predicts as the next sentence, if it's correct or not. I think it can get more complex if you go into these things, but the essential idea I think is well understood. I hope for me it is, I think, and I hope it's equally for you. Let's just go and just look finally at this. Maybe now it makes more sense. So this is the pre-training, and again we have the masked input. We see unlabeled sentence A and B pair. So we get them as a pair. All of that is pushed in. Again, we mask randomly an input and we try to predict it, and then we try to predict the next sentence. All of that happens here. All of that happens here. Again, we see these special tokens here and here, and then we go to the pre-training, which follows the same architecture. I assume here we just basically give it the input that it gets, the actual data that is pushed through that architecture of fine-tuning is task specific. So as it gets to change the weights of the model, it is actually tweaking those weights towards what I would assume is labeled, maybe this time, labeled information or data that is trained on for that task, and it will get that model to modify to perform much better on that specific task, like sentiment analysis. Okay, so before we move to the next one, again, two quick concepts I want to cover. Let's go for the first one. So it's called the stochastic gradient descent. I hope I read it right. Stochastic gradient descent. Again, just read it. You might not get it from the first time. It will be mentioned in one of the papers, and I think it's important for us to understand why they bring it up and what they talk about there. So in general, the stochastic gradient descent, or SGD in short, is an optimization technique used in machine learning to minimize errors in predictive models. Unlike regular gradient descent, which uses the entire dataset to calculate the gradient and update model parameters, SGD updates the parameters using only one data point at a time. This makes it faster and more efficient for large datasets. Although it can be noisier and less stable, SGD helps find the optimal values for model parameters to improve the accuracy of predictions. So it's a variation of the gradient descent, the standard one, and the way I understand it, it goes in sequence, parameter per parameter, rather than just going across all parameters. Makes things faster, easier, It might be unstable. This is what they're mentioning here, but I assume using that, you can use it when the benefits outweigh the risk of that instability. So that's one idea to keep in mind. The other one is few-shot learning. So I'll just read this quickly. No need to dig deeper in it. Again, all of this, you'll have it, the links. You can read in these concepts, but we want to understand in general, what's the idea of a few-shot learning. So few-shot learning is a machine learning framework in which an AI model learns to make accurate predictions by training on a very small number of labeled examples. It's typically used to train models for classification tasks when suitable training data is scarce. Okay, few-shot learning, FSL, is a subset of what is sometimes referred to more generally as N-shot learning, a category of artificial intelligence that also includes one-shot learning, in which there is only one labeled example of each class to be learned, and zero-shot learning, in which there is no labeled examples at all, while one-shot learning is essential, just a challenging variant of few-shot learning. Zero-shot learning is a distinct learning problem that necessitates its own unique methodologies. So, okay, zero-shot is something else. In principle, few-shot learning aims to emulate the human ability to learn from a mere handful of examples. This stands in contrast to conventional supervised learning, which typically uses many hundreds or thousands of labeled data points across many rounds of training to each AI models to recognize classes of data. While powerful supervised learning is impractical in some real-world settings, obtaining labeled example is often difficult due to prohibitive costs. The domain-specific expertise needs to annotate data correctly, or in scenarios like unique handwriting, rare disease, or endangered and newly discovered species, the scarcity of existing samples. While certain specific algorithms and neural networks architectures have achieved notable success in few-shot learning tasks, few-shot learning is defined by the nature of the learning problem rather than by the use of any specific method or model structure. Few-shot learning methods range widely from adapting to pre-trained models or use a similar task in using generative models to create new samples, to meta-learning methods that train models to generalize well to new classification problems and different classes of data rather than perform any one specific task. Okay, so the way I think we need to understand it is simply it's a way of training a model by giving it examples. I've seen it in fine-tuning, but here they use it in actually training the model. They're talking about 3 of them. Zero-shot learning, which is something apparently like unique and it has its own methodology. And then you have single-shot learning, which is simply giving the model one example to go off and generalize based on it. And then you have few-shot learning. The biggest problem they're solving with this kind of method is that scarcity of data is there in certain cases. And I think data is a bigger problem of in AI than the actual technology, I think, at times, from reading into these things. So they compare it here to supervised learning, where you have the data and you basically push it in. You have validation data, you have basically training data, validation data, and testing data. You push that, you do the supervised training process, and then you get these kind of the true positive, false positive, true negative, false negative kind of matrices that could tell you as you supervise the model in its training if it's getting things right or wrong. I just think that that general understanding now out of reading this is what is needed. Simply it's training based on examples. So let's continue to one more concept and then we'll jump straight into the next paper, which is the next major thing that happened after the BERT in 2019 and up till 2024. So I'm going to cap it until 2024, mid 2024 actually. One more thing I want to show you before we jump to the next paper. So let's go here. This is the GPT-4, so OpenAI's GPT-4 architecture, transformer architecture. It's like exactly the same transformer architecture we reviewed from 2017. And I think GPT-2 is where OpenAI started to showcase to the public their models. And also one more interesting thing is they were transparently sharing the architecture. And I think here, okay, they didn't have anything to really hide, especially that this is based on the Attention is All You Need paper. So just for you to understand, even up till the moment that we had GPT-2, we had the transformer architecture, still the main AI architecture used in these models. So let's move on. Now, here things will be much faster because I think, the transformer architecture was significant in 17, BERT was really significant in 19. Now we're just going to get some hints of what happened following BERT. At least what really I think matters for all of us to understand. Language models are few-shot learners, and this is a paper in July 2020. So we got BERT in 2019, and then this came from OpenAI. So let's go through the abstract and see what we get in this paper. Again, here I'm gonna get snippets of important things, not the whole thing, because things didn't move between paper to paper as significantly as you think, even beyond the 2017 transformer architecture. Recent work has demonstrated substantial gains in many NLP tasks and benchmark by pre-training a large corpus of text followed by fine-tuning on a specific task. So you can see here they're referring to what BERT came up with in 2019. While typically task-agnostic in architecture, this method still requires task-specific fine-tuning datasets of thousands or tens of thousands of examples. By contrast, humans can generally perform a new language task from only a few examples or from simple instructions, something which current NLP systems still largely struggle to do. Here, we show that scaling up language models greatly improves task-agnostic, few-shot performance, sometimes even reaching competitiveness with prior state-of-the-art fine-tuning approaches. Specifically, we train GPT-3. So this is the paper that brought GPT-3 to the picture. An auto-regressive language model with 175 billion parameters. If you remember, when we were looking at BERT, we're looking at BERT Basic and then the actual full one. And we're talking about 110 million parameters for BERT Basic to compare it to GPT-2. And then I think the full one was around 200 something million. I forgot. But you get it why I said that's like a drop in the bucket. Even this one now, GPT-3 is a drop in the bucket of the models that we have today. So the growth and the number of parameters they're using to train these models is exponential, at least until this point. Maybe in the future it will not be the same because now we know we can do much better with smaller models. Just to keep this in mind of how things were moving year over year when it comes to these models. So again, specifically we train GPT-3, an auto-regressive language model with 175 billion parameters, 10x more than any previous non-sparse language model, and test its performance in a few-shot setting. For all tasks, GPT-3 is applied without any gradient update or fine-tuning. So they're not doing any fine-tuning for this model. With tasks and few-shot demonstrations specified purely via text interactions with the model, GPT-3 achieves strong performance on many NLP datasets, including translation, question answering, and close tasks, as well as several tasks that require on-the-fly reasoning or domain adoption, such as unscrambling words, using a novel word in a sentence, or performing 3-digit arithmetic. At the same time, we also identify some datasets where GPT-3's few-shot learning still struggles, as well as some datasets where GPT-3 faces methodological issues relating to training on large web corpora. Finally, we find that GPT-3 can generate samples of news articles which humans evaluators have difficulty distinguishing from articles written by humans. We discuss broader societal impacts of these findings and of GPT-3 in general. So, in a nutshell, they said things were happening as BERT came out with their paper about bidirectional models that are done through pre-training and then fine-tuning. They said it's not working like humans do when it comes to dealing with language and natural and neural processing. We're going to do something else, which is the few-shot learning, which we read about. We know what few-shot. So basically, we train the model by giving it examples rather than anything else. And we are not fine-tuning this model. And later on, they say, obviously, this is a huge model. They say that it does more tasks, does tasks that before which were not done by the previous models. And even it does at this level, at that stage, 3-digit arithmetic. And this is the paper where they dropped GPT-3, and at the end it says that GPT-3 actually did news articles that the people who were evaluating this model couldn't tell that this was written by AI or a human. And I think this is the point of history. This is the paper where actually AI became mainstream. Because once GPT-3, if you remember, I think most of us remember, once GPT-3 was hitting the news, when OpenAI made it public and gave people access to it, GPT 3.5, just for me, it's like yesterday it was there and we were using it as a model. It was the time where AI models became something that most people are interested in, most people are talking about. Even here, they mention at the end, they're going to discuss the broader societal impacts, because I think they realized at that point that they have achieved the level of AI models that will probably scare people and where they need to start thinking about safety, maybe not so deeply at that level. Now it's totally different with OpenAI, everything's about safety, but here at least they realized we have something on our hands that we will push to the public that they can definitely do a lot with. Okay, so let's carry on. So this is the legend if you want to go and do your own reading. Let's read the introduction. Again, we just want to get the concept of what happened with GPT-3, and later on we will move to other papers that just gives us those kind of significant points of time when something came out and changed how we know AI models as they look today. Okay, so let's go to the introduction. Recent years have featured a trend towards pre-training models representation in NLP system applied in increasingly flexible and task-agnostic ways for downstream transfer. First, single-layer representations were learned using word vectors and fed to task-specific architectures. The RNNs, in the first video we talk about what RNNs are, so you can refer to that or just do a quick search on your own, with multiple layers of representations and contextual state were used to form stronger representations, though still apply to task-specific architectures, and more recently pre-trained recurrent and transformer language models have been directly fine-tuned, entirely removing the need for task-specific architectures. Basically, they're just telling us the history from transformer architecture and then what BERT gave us all. This last paradigm has led to substantial progress on many challenging NLP tasks, such as reading comprehension, question answering, textual entailment, and many other, and has continued to advance based on new architectures and algorithms. However, a major limitation on this approach is that while that architecture is task agnostic, there is still a need for task-specific datasets and task-specific fine-tuning. To achieve stronger performance on the desired task typically requires fine-tuning on a dataset of thousands of hundreds of thousands of examples specific to that task. Removing this limitation would be desirable for several reasons. So I think here what they're talking about that yes, we did a great job with the pre-training and fine-tuning approach. The problem is, still with that approach, you do the unlabeled data type of pre-training for the model, the MLM, and then you're going to have to move to the fine-tuning. Now, once we move to the fine-tuning, BERT did it for 11 tasks, if you remember. So for each task to fine-tune it, there's lots of work that has to go when it comes to the data. So it's less of a problem of the resources, I think, of training. It's just of the preparation work that they need to do all of these thousands of examples for each task and then get the fine tuning done. So it's a big headache, it's a big challenge, and you can call it even a barrier to these innovations just by doing it using that methodology. Now they're going to propose something different, which we know is based on the few-shot learning. First, from a practical perspective, the need for a large data set of labeled examples for every new task limits the applicability of language models. There exists a very wide range of possible useful language tasks encompassing anything from correcting grammar to generating examples of an abstract concept to critiquing a short story. For many of these tasks, it's difficult to collect a large supervised training dataset, especially when the process must be repeated for every new task. Second, the potential to exploit spurious correlations in training data fundamentally grows with the expressiveness of the model and the narrowness of that training distribution. This can create problems for the pre-training plus fine-tuning paradigms, where models are designed to be large to absorb information during pre-training, but are then fine-tuned on very narrow task distribution. For instance, they're referring again to a resource. Observe that larger models do not necessarily generalize better out of distribution. There is evidence that suggests that the generalization achieved under this paradigm can be poor because the model is overly specific to the training distribution and does not generalize well outside it. Thus, the performance of the fine-tuned models on specific benchmarks, even when it is normally or nominally at human level, may exaggerate actual performance on the underlying task. I think the way I understand this, they're simply saying, yes, we give lots of credit to that fine-tuning process. Still, it is so limited or so narrow that you cannot generalize. And it's a big thing when it comes to how you apply those AI models to real-life tasks and how you generalize them. Basically, they're working their way to having real artificial intelligence of the way they train these models. And basically, they're arguing here that yes, although when you do the fine-tuning per task, it operates to a certain extent well for that task, which even here there is questioning. It might, like if you test it differently, it might not give the performance we are basically pre-training for these fine-tuned models. We have to do it differently, basically, to have it more generalized as a model and as an approach. And just they remind that every time you need to add a new task, you'll have to go through that painful process of putting all of these examples together. And the concept of tasks, I think this is what they're talking about, is very limiting because the combinations of tasks that such models can be used for is countless, and it will always, like, using that kind of methodology will always keep these models limited. So they give even a third reason. Humans do not require large supervised datasets to learn most language tasks. A brief directive in natural language, example, please tell me if this sentence describes something happy or something sad, or at most a tiny number of demonstrations. Example, here are 2 examples of people acting brave. Please give me a third example of bravery. Is often, let's continue, we'll go back to the figure later, sufficient to enable a human to perform a new task to at least a reasonable degree of competence. Aside from pointing to the conceptual limitation in our current NLP techniques, this adaptability has practical advantages. It allows humans to seamlessly mix together or switch between many tasks and skills. For example, performing addition during a lengthy dialogue to be broadly useful. We would someday like our NLP systems to have this same fluidity and generality. One potential route towards addressing these issues is meta-learning, which in the context of language models means the model develops a broad set of skills and pattern recognition abilities at training time, and then uses those abilities at inference time to rapidly adapt to or recognize the desired task. Okay, they have an illustration which we'll go back to. Recent work attempts to do this via what we call in-context learning, using the text input of a pre-trained language model as the form of task specification. The model is conditioned on a natural language instructions and or a few demonstrations of the task and is then expected to complete further instances of the task simply by predicting what comes next. While it has shown some initial promise, this approach still achieves results far inferior to fine-tuning. For example, achieves only 4% of natural questions, and even, okay, this is again, I think, a benchmark, result is now more than 35 points behind the state of the art. Meta-learning clearly requires substantial improvement in order to be viable as a practical method of solving language tasks. Another recent trend in language modeling may offer a way forward. In recent years, the capacity of transformer language models has increased substantially from 100 million parameters, I think this refers to BERT, to 300 million parameters, to 1.5 billion parameters, to 8 billion parameters, 11 billion parameters, and finally 17 billion parameters. Each increase has brought improvements in text synthesis and or downstream NLP tasks. And there is evidence suggesting that log loss, which correlates well with many downstream tasks, follows a smooth trend of improvement with scale. Since in-context learning involves absorbing many skills and tasks within the parameters of models, it is plausible that in-context learning abilities might show similarly strong gains with scale. So the way I understand this, I think they're sacrificing certain aspects to challenge the current way of, at that time, of how the state-of-art models are working with pre-training and fine-tuning, just to suggest a new way forward. So they mentioned a couple of benchmarks where actually the model, at least the way they are suggesting, is behind. But on top of that, they say this is the promising way of the future, where we get these models to generalize and based on examples and context, able to basically perform better across different tasks. So basically, I think this is the part where we say it's like the real generative artificial intelligence is coming to fruition in their ideas. They are referring to the what we skipped already, which is this visual. So here, if we look at, this is an outer loop, okay, this is an inner loop. Here you have in-context learning. So this is what they refer to. This is what they're suggesting as a way forward compared to pre-trained large models and then fine-tuning it. They're still working with these pre-trained large models. It's a success that they confirm. You get unlabeled data, you pre-train the model, and you get that model ready to do tasks. Now, before we had to fine-tune it, now they're suggesting what they call in-context learning. And here you have multiple sequences, and this is an arithmetic sequence, and it's just giving examples of calculations. They mentioned that up to 3 digits, I think, it's doing arithmetic. So 5 plus 8 is 13. So basically, this is the few-shot learning. They call it in-context learning, but this is the few-shot learning. And this is one sequence, for example, is for numbers. This sequence is for fixing, I think, the grammar, or just simply predicting the word from shuffled letters of that word. So you can see goat, they just fix the O and they put it in the right place. So it can actually be the spell check type of task. So you have snake, you can see here how it's written, bird, and okay, so all of these are example. And then the third sequence in context learning is a translation. So thanks is merci, hello is bonjour. This is French language here. So you have an inner loop. So I think it does just goes through this, does go through this and through this. And then it goes through an outer loop, basically shuffles through all of these in context learning or few shot learning kind of examples. And this way you basically get a model that is able to generalize based on looking at these few shot examples within each sequence across the whole sequence that is pushed to the model. So, and from the looks of it here, they're suggesting, or they're saying it goes into, you know, an input and an output. So for the example in arithmetic, 5 plus 8, you get the output for it is 13. 7 plus 2 is 9. And then goat and goat in the right way, snake and snake, fish and fish. And then the translation one is thanks and merci, hello and bonjour. Okay, let's read a couple of things following that. Let's just now read what goes under this diagram here. During unsupervised pre-training, a language model develops a broad set of skills and pattern recognition abilities. It then uses these abilities at inference time to rapidly adapt to or recognize the desired task. So just because it has that ability, it can recognize and adapt and give the response for that desired task. We use the term in-context learning to describe the inner loop of this process, which occurs within the forward pass upon each sequence. The sequences in this diagram are not intended to be representative of the data a model would see during pre-training, but are intended to show that there are sometimes repeated subtasks embedded within a single sequence. Okay, so this is not how it actually happens, and it's there just that they show the idea. And the idea, I think they put this example is just an easy way to understand what they're talking about, which makes sense. I would be able to explain this to someone that this is what is the in-context learning or the few-shot learning, and how OpenAI used it on top of the pre-trained model in GPT-3 to give it that generalization and the ability pushed from so many examples that it was introduced to the model as part of the training of that model. So let's carry on to see if there's important things we have to cover before we move forward. So here they're just saying, in this paper, we test the hypothesis by training a 175 billion parameter autoregressive language model, which we call GPT-3, and measuring its in-context learning abilities. Specifically, we evaluate GPT-3 on over 24 NLP datasets, as well as several novel tasks designed to test rapid adaptation to tasks unlikely to be directly contained in the training set. So basically, they did training or testing for things that are well-known benchmarks, and they had some novel tests that they introduced just to see what they're talking about. Is it happening, like the generalization and addressing tasks? Is it part of the model now? Can the model react as they claim? So this is just something they're informing us with. We evaluate GPT-3 under 3 conditions: few-shot learning. So this is a condition of evaluation, okay, or in context. So, okay, they're using it interchangeably, either few-shot learning or in-context learning, where we allow as many demonstrations as will fit into the model's context window, typically 10 to 100. And then B, one-shot learning. So they're using also the one-shot learning method, where we allow only one demonstration. And then, so they're using the zero-shot learning, where no demonstrations are allowed and only an instruction in natural language is given to the model. GPT-3 could also, in principle, be evaluated in the traditional fine-tuning setting, but we leave this to future work. So they're not going to evaluate through fine-tuning. What they're saying is they're going to give it either multiple examples, so the few-shot learning, they will give it one example as a part of the training, or no example, just they use natural language to describe the task that is given to the model and see how they perform across the 3 of them. For the multi-shot, they're talking about 10 to 100 examples. And then the one shot is obvious enough, and the zero shot, I think, is obvious enough as well. So let's carry on quickly. The figure that we've looked at illustrates the conditions we study and shows few-shot learning of a simple task requiring the model to remove extraneous symbols. Figure 1.2 illustrates the condition we study. So we're going to go to figure 1.2 quickly to look at that if it's interesting, and shows few-shot learning of a simple task requiring the model to remove extraneous symbols from a word. Model performing improves with the addition of natural language task description and with the number of examples in the model context, K. Few-shot learning also improves dramatically with model size, though the results in this case are particularly striking. The general trend with both model size and number of examples in context hold for most tasks we study. We emphasize that these learnings curves involve no gradient updates or fine-tuning, just increasing the number of demonstrations given as conditions or as conditioning. Okay, so let's go to that figure quickly. So here they're showing us, okay, number of examples in a context. So the more we go to the right, the number of examples or shots is increasing. And this one is the accuracy. So if it goes up, accuracy increases, goes down, accuracy decreases. So 0 is the point where you have 0 shot kind of testing or training. So you can see we have the different parameters. So we have basically a color, a blue for the 175 billion parameter. This is GPT-3, 13 billion parameter and 1.3 billion parameter. And it seems across of them, the more examples the model get, it actually is improving in terms of accuracy. And it seems to me also that the biggest contributor to improvement in performance is the size of the model. Yes, it is improving with the number of examples, but I think this is something they're hinting to, that the model size, the number of parameters, is a big influencer to how these models perform in terms of accuracy of predicting outcomes or outputs. So we can see this here when it comes to the 175 billion parameters. And here they're talking, this is like natural language prompt and no prompt. And okay, so this is the single shot here. So once you have no examples, a prompt, you get some kind of accuracy. It's a very low one, less than 10%. And at the peak performance of this model, 175 billion parameter, we have above 60% accuracy. Today, it's much better. I think we all realize that. But at that time, 2021, where AI broke loose and people went crazy about it, this actually what did it for people. This was the best thing, best technology we had at our hands at the time. Excellent. So let's continue a little bit before we move forward. Or is there something interesting here? Okay, broadly, the NLP tasks achieve promising results. I'm just going to scan through that for you not to waste time. Again, here we're talking about performance and benchmarks, so I will not go through that. So again, talking about, okay, all of this is performance talk. We can skip that. We also undertake a systematically study of data contamination, a growing problem where training high capacity models on data sets such as a common crawl, which can potentially include content from test datasets simply because such content often exists on the web. In this paper, we develop systematic tools to measure data contamination. And okay, they're talking about how do they put together, cleanse, improve I would say, the quality of the training datasets. Okay, they carry on here about the model size. Okay, let's go to the approach quickly. So our basic pre-training approach, including model, data, and training, is similar to the process described in a different paper. I assume that's BERT when it comes to the pre-trained model, which is 19. I don't know if it's 2019. Anyways, with the relatively straightforward scaling up of the model size, data set size, and diversity and length of training, our use of in-context learning is also similar to, okay, this is definitely a different resource. But in this work, we systematically explore different settings for learning within the context. Therefore, we start the section by explicitly defining the constraints, the different settings that we will be evaluating for GPT-3. Okay, so they're just giving us what they do. So let's just high level, I think we understand the idea of what they're doing here compared to what BERT had. So they've dropped the fine-tuning and they focus on, as part of the training of the model, they use the in-context or few-shot learning to make it generalized and work better for tasks, general amount of tasks or bigger amount of tasks. In certain areas, they said it was reducing the performance quality of the model in certain specific tasks. But as a way forward, they think this is the best bet for us to go with when it comes to developing these models. So let's just go quickly on fine-tuning. It has been the most common approach in recent years and involves updating the weights of the pre-trained model by training on a supervised dataset specific for a desired task. And they said this is something they're not going to do. Typically, thousands to hundreds of thousands of examples. Okay, the main advantage of fine-tuning, so and so. Okay, they mentioned before that, as I just said, in certain tasks, fine-tuned model are doing better than ChatGPT 3. So here, I don't know why they're talking again about that. In this work, we do not fine-tune. So they just want to make it crystal clear. When it performs, I would assume, really well and better than BERT, it's not fine-tuned. It's simply trained on the unlabeled data, which is basically the masked language model, and then the few-shot learning as part of that training process. So here they talk about the few-shot and the one-shot. I don't think we should go again and read it. And here you have a diagram showing you a different way of looking at zero-shot, one-shot, and few-shot. I'll give you the link for the paper, you can read through it. But I think GPT-3 was a very significant moment of the history of AI, similar to the BERT, similar to the OG of papers, which was Attention's All You Need in 2017. The only thing I think GPT-3 did is that it broke from that limited number of tasks. So it's not something anymore at this moment of time in 2021. An AI model is designed behind a tool that does a specific task like translation, a specific task like something else, sentiment analysis. Now you have one model that can serve across so many tasks based on the way they're training it. At that moment of time when they did it, they had to sacrifice the quality of the output or the outcome for certain tasks compared to the fine-tuned model at the time. But they had clearly a deep belief that this is the way forward for these models to reason more closely to humans. And I think this is a bet we know they won over what BERT did and what later on BERT tried to do when it comes to improving what they have as a model. Google, when I say BERT, it's Google, what they tried to do to improve their model and compete with OpenAI. But I think this is really the significant moment for AI in general, this paper we're looking at. This is the significant moment for OpenAI as a company. And this is where the floodgates of AI in general opened online and on the news and everywhere. So very interesting one. Let's move to the next paper, and now we're gonna look a little bit on visual. And by the way, you'll be surprised that visual models, so things that give us images like DALL-E, like whatever model you are using for that, are not so much different when it comes to the transformer architecture. They call it the visual transformer, compared to what we already know. So that's great. I just want you to understand how these started coming in and what's the difference there, at least for us to be always aware of how the generative text-based AI models work, but also how the visual ones work. So in the future, any paper we tackle, we have that fundamental understanding as a group and we can grow our knowledge from there. So let's go to the next paper, Learning Transferable Visual Models from Natural Language Supervision. Okay, so we're not, again, going to cover the whole thing, just to get really what matters for us to understand out of this. State-of-the-art computer vision systems are trained to predict a fixed set of predetermined object categories. This restricted form of supervision limited their generality and usability, since additional labeled data is needed to specify any other visual concepts. Learning directly from raw text about images is a promising alternative which leverages a much broader source of supervision. We demonstrate that the simple pre-training task of predicting which caption goes with which image is an efficient and scalable way to learn SOTA image representations from scratch, and on a data set of 400 million image text pairs collected from the internet. After pre-training, natural language is used to reference learned visual concepts or described new ones, enabling zero-shot transfer of the model to downstream tasks. We study the performance of this approach by benchmarking on over 30 different existing computer vision datasets, spanning tasks such as OCR, action recognition in videos, geolocalization, and many types of fine-grained object classification. Okay, so here they're saying that originally these visual models worked on mostly classification. So basically, let's say we give a machine learning, mostly I would call it machine learning more than AI, pictures of a dog. as an example, and I label it. I say, this is what you call a dog, and these are the pictures. And I give it something else for bags, handbags, for example, and 100 pictures of handbags, and I label it as handbags. Later on, when I give it the picture of a different handbag or different dog, it will high probability response with the label. This is a dog or this is a handbag. Now they're saying the combination of text when it comes to image and how you break down an image and tell what's there. And here they're hinting to the usability of the technology of attention or the transformer architecture in general in images. So I think they're trying to take a shot with working on that. So let's read on, and then we'll see what this is really about. So introduction and motivating work. Pre-training methods which learn directly from raw text have revolutionized NLP over the last few years. So here they're talking about all the papers, everything that happens, and I think some of them are what we read about BERT and GPT-4. So they're saying this way of pre-training, fine-tuning, or later on pre-training and index learning have revolutionized the models that we deal with. So let's carry on. Task-agnostic objectives such as autoregressive and masked language modeling, the MLMs we talked about, have scaled across many order of magnitude in compute, model capacity, and data, steadily improving capabilities. The development of text-to-text as a standardized input-output inference has enabled task-agnostic architecture to zero-shot transfer to downstream datasets, removing the need for specialized output heads or dataset specific customization. Flagship systems like GPT-4 are now competitive across many tasks with bespoke models while requiring little to no dataset specific data training. So again, here they're talking about the success of OpenAI in doing this without the fine-tuning or having those kind of per task complex labeled data that we use for fine-tuning and the generalization ability of GPT-4. These results suggest that the aggregate supervision accessible to modern pre-trained method within web-scaled collections of text surpass that of high-quality crawled labeled NLP datasets. Okay. However, in other fields such as computer vision, it is still standard practice to pre-train models on crawled labeled datasets such as ImageNet. So ImageNet, again, all of these are standard datasets that you can use to pre-train models. And here they ask the question, could scalable pre-training methods which learn directly from web text result in similar breakthrough in computer vision? Prior work is encouraging. Okay, so here they go over some history over 20 years ago. Okay, so here they're talking about the history of vision when it comes to machine learning. I think we'll skip that. We'll go back to this visual later on. Let's carry on with okay, here they're talking about, again, continuing the history, and they're talking about the concepts, historic concepts of image machine learning models that were working. And I have a video about machine learning where I talk across the convolutional networks, where I touch a lot about these things. If you're interested, you can watch it as well. All of these kind of videos I'm going to keep in one single playlist, by the way, for easy reference for all of you in the future. So they carry on reading about this. Okay, so let's actually go to the model, and then we'll go to the approach. I think we look at this diagram, we go to the approach, it will be much easier to understand what they've done, and then we go back to the image, it will be perfect. This is how I usually do it. So if you remember, and if you refer to that video, but I can quickly give you an idea, images are, we know they are pixels, but the best way to imagine it, it's actually how it is. Each pixel or each part of the image is actually some numbers. It's a matrix of numbers, right? And in theory, you can create a matrix out of it and you can manipulate it through a neural network of some sort. Now, there's more into this. There's what is called the convolutional neural networks. It's a well-known type of network where you take an image, you cut it into pieces, and you take each part of that image and you call that a convolution. You run it through what they call kernels, which is basically manipulations. And the easiest way I describe them, it's either making that part of the picture as, let's say, more contrasty or something else. And you do all of that through mathematical manipulations of these matrices of numbers. So basically, any image, you can take it and translate it into numbers, and any matrix of numbers, you can take it and make it back an image. So here we have a number of images. It goes through an image encoder. So it's similar, I would call it the image encoder, like the embedding of images. So we take that and we create a matrix, and clearly here it's one-dimensional matrix of these images into numbers. And then here you have Pepper the Aussie Pup. So this is a description or the label for this dog. It goes also into a text encoder. And then here we get another single dimensional matrix, which is the embedding or the encoding, the outcome of the encoding of the label. And all of these two single directional matrices are basically joined in a multi-dimensional matrix. I assume it's multi-dimensional, not only two-dimension. And here, I think the idea of this, what they call contrasive pre-training, is that you take the label and you take the image and you actually create a kind of matrix that you can potentially later on use in self-attention with weights. But basically it's mixing the text part of the label and the image part of how we convolutionize an image into a number matrix, a numbered or mathematical matrix. Okay, so then number two here, so this is number one. Apparently you create that kind of matrix which is marrying the text of the label and the image. Two, we go to create a data set classifier from label text. So here, plane, car, dog, bird, a photo of a, okay, so here you have an object to predict. Basically it goes to a text encoder. Okay, that's fine. And three, use for zero shot prediction. So here you have a picture of a dog. It goes to an encoder, and then we mix the prediction of the word with the prediction. So this is coming in as a single number for the image. So okay, so what I assume I understand from this is this kind of trained model or pre-trained model is coming in here. So these numbers or weights or whatever I get as a result enable us to predict this variable here or object, not only based on logic in text, but it's basically both logic in text and what we get from the image based on what we pre-trained here. So this is, I think, from just looking at the diagram, this is how we are doing things in visual. And just to remember, this is in, again, 2021. So we mix the ability to do what we did with GPT-3. So we mix the way we deal with text and the models at that time, the state of the art or the flagship was GPT-3. And then we mix it with convolutional neural networks, or how we handle images in these kind of networks. We put them together and we get better ability in prediction. Here we are leveraging even basically the brains of the text-to-text type of model and really doing things with pictures. Here it's predicting what is in the image. So let's read this quickly. While standard image models jointly train an image feature extractor and a linear classifier to predict some label, Clip jointly trains, they call it Clip, jointly trains an image encoder and a text encoder to predict the correct pairing of batch of image and text. So the data is a batches of pairs of image and text. Training examples. At test time, the learned text encoder synthesizes a zero-shot learn classifier by embedding the names or descriptions of the target dataset classes. Okay, so I think I got it right. You can read it on your own. I don't want to put more time here. I think it's interesting if you want to read more and more about how it performed and what they got and the kind of vision transformers they used. This is a long thing, and they talk about SOTA here, and you can see actual dataset examples and the performance, all of that. You know, before I move on to the final papers we're going to look at, I think this is the important part we take away from this. So when they did this in 2021, they introduced, although they're saying it's not new, but they basically tried to, rather than do the convolutional neural network machine learning method of getting a model to predict an image just based on pixels, the numbers behind that image, they actually did it with text. So you can, at that time of this paper, you can use that model, give it an image, and ask it a question. It will be able to predict that that image or what it has, even because they mixed it with the idea of GPT-3, which went with the single shot, zero shot, and few shot learning or in context learning. I think it can do that to predict the content of the image or the object in the image without actually giving it a prompt. So a zero shot, because when we were reading, they mentioned zero shot multiple times. But I think it's very important that in 2021, apparently people did work that led up to this, using different terminology, different motivations, as they call it. We started basically mixing the visual transformer with the transformer architecture of text-to-text models that we know, where we get them to marry in a trained model that today it makes sense if you look at any model we use to generate images, because you give it text and you get an image. How it does that is, I think, through this matrix that we train here. So this is what we get out of training model of text and image. So we give it that kind of, this is how the image looks, the pixels. And again, remember, we're talking about the transformer architecture and even the visual transformer, which in images, it looks at the attention of a pixel compared to the other pixels. The same goes for text in a sentence, word to the context of the sentence. So we marry them in a trained model that I think at some point took us to a place where we give a prompt, we get an image, we give an image, we get an answer of what that image contains. So, and they do it through this marrying text transformers to visual transformers. I think if we get this idea, you know how things moved from what we had in machine learning, where we were predicting or classifying images based on giving 100 number of dog images, a label of a dog, and then getting that answer later on when we give it a dog, which was very limited. And then they got the idea, oh, why don't we work with the transformer architecture as number one in a visual transformer, and why don't we also make use of what GPT-3 changed when it comes to the fine-tuning problem, and we marry both. So we take the transformer matrices that contain the information, the attention information of the text, and add it on top of that to the visual transformer. Again, these are numbers. You can manipulate both, and we can create a model based on both sources. And we create a model that could actually do that without the machine learning part and having, again, the problem of data and training and computation. Now, they say it's heavy computationally, it's slower to do these things, but at that stage when they came up with it, it was a breakthrough for the future of image and AI models altogether. Okay, let's carry on. So now I'm going to give you just 4 papers. You'll have to bear with me, but these, like, I'll spend 5 minutes on each, even less. But I think some of them have interesting things, especially the last one. It has a really significant thing that I think all of us should read, and it's just very interesting to look at. But here we are going to look at this quickly. This is a paper, again, in 2021 by Google. An image is worth 16 by 16 words. Okay, so transformer for image recognition at scale. Again, image transformers, visual transformers, but I think some parts better clarify the concept of image transformers compared to the paper we just covered now. So let's read the abstract pretty quickly here. While the transformer architecture has become the de facto standard for natural language processing tasks, again, the same thing everyone talks about, its application to computer vision remain limited. In vision, attention is either applied in conjunction with convolutional networks, which we talked about, or used to replace certain components of convolutional networks while keeping their overall structure in place. We show that this reliance on convolutional networks is not necessarily, and a pure transformer applied directly to sequence of image patches can perform very well on image classification tasks. So what they're saying is we don't really need to just rely on convolutional neural networks. That's not necessary. And they're referring to that their alternative method is just getting really well classification tasks compared to what we get in machine learning, as we discussed before. When pre-trained on large amounts of data and transferred to multiple mid-sized or small image recognition benchmarks, so these are well-known benchmarks, Vision Transformer attains excellent results compared to the state-of-the-art convolutional networks while requiring substantially fewer computational resources to train. So there's a big advantage in this compared to the conventional convolutional neural networks. So here they go through the introduction of what they did, and it is very interesting to always see that the first paper they refer to is the transformer architecture. So here they're saying all of this is becoming the standard. And here, if you look at the papers they're referring to, definitely you're going to see BERT, I assume, and you're going to see other things maybe already covering concepts we looked at. So let's continue here. Inspired by the transformer scaling success in NLPs, we experiment with applying a standard transformer directly to image. We've already looked at that with fewest possible modifications. To do so, we split an image into patches. This is the convolutional part of it, the standard convolutional approach to things, and provide a sequence of linear embeddings of these patches and input to a transformer. Okay, so this is what the previous paper showed. So you see at that time companies were trying to do some of the same thing in different tweaks to get to beat people or the market to that model that works better with images. Image patches are treated the same way as tokens or words in the NLP application. We train, so the patch is part of the image. You could see in the previous diagram we looked at. We take into a number, so it's basically a token of its own. We train the model on image classification in supervised fashion. Okay, so they say when training on mid-sized data set, such as ImageNet, without strong regulations, those models yield modest accuracies of a few percentage points below ResNets of compatible size. This seemingly discouraging outcome may be expected. Transformers lack some of the inductive biases inherent in convolutional neural networks, such as translation equivalence and locality. Okay, so here they talk about some of the related work. You'd expect here the first one to be the transformer architecture. You expect to find BERT here. I'm sure they have lots of things around convolutional neural networks and machine learning, and where it took the at that time the current state of predicting or classifying images. So this is the diagram of the vision transformer. Here they have something called the transformer encoder. This is the transformer encoder. We're going to go into it quickly. But the first thing you can see here, it looks like something, isn't it? And for me, just looking at it, it looks nearly just like the transformer architecture encoder that we looked at in the original 2017 Attention is All You Need paper. And that just shows you the impact of that paper and how much most things till for this paper's sake, 2021, were exactly the same as 4 years before that in 2017 when it comes to the technology of these architectures of these models. So let's quickly go to the logic of this. You have an image, you break it down into patches. Each patch, obviously this is just to explain it in an easy way. I would assume a patch is even as close as a pixel or a couple of 4 pixels maybe. And you take all of these patches, you basically get the embedding version of a patch. So you get that number that represents that patch. You get also the position of it. So you have, let's say, 9 boxes in the original image. So we take an image, we break it down to 9 boxes. So we number them 1 to 9. So you take the number that represents the patch, specific patch, basically the embedding version of the text, and then you take the sequence, you put all of them together as we see here. Again, exactly what happens in the transformer when it comes even to text. Then you push it to the encoding. If you look at the encoding, this is the embedded patches, basically what we got here. Okay, we push it to a normalization similar to the transformer architecture. We take it into a multi-head attention. So we take those numbers and we try to correlate different parts of that image to each other. So we're doing the same what we did with text, we're doing it with image. And again, remember, in reality, the patch is not as big as the example here. And then obviously we have the normalization, the feed forward. Here they call it MLP, which we will see what that is. Then you have the feed forward network, quote unquote, and then you get an output. And that helps with taking this further. I think today you can take it to do images actually even. But here you're trying to somehow predict a word. So here you can see the output of the transformer. This is the MLP head, and then you get a classification, which is a bird, ball, car. So this is how it works. So here they say we split the image into fixed size patches, linearly embed each of them at position embedding. So the concept is the same about the embedding or the turning the patch into a number, and feed the resulting sequence of vectors to a standard transformer encoder. So they call it a standard transformer encoder. In order to perform classifications, we use the standard approach of adding extra learnable classification tokens. Okay, so this is just a tweak to this. The illustration of the transformer encoder was inspired by, again, they keep referring to the attention is all you need. So that's inspired by that. Here they talk about the method, basically the vision transformer, how it works. You can read the details on your own, but I think you get the idea, right? It's really turning an image to numbers and then running it through the attention heads somewhat, and the transformer architecture exactly the same. And from the output, you can actually get a prediction or classification, maybe is the more accurate term here. And by the way, I don't know why they're not mentioning MLP in detail, which we saw here. MLP is what they call a multi-layer perception. And the way I understand it is similar to the feed-forward network, that basically you process something through these matrices through it, and you get that kind of classification out of it. So it's just a network, but they call it multi-layer perception. So it's a multi-layer network that helps you get all of this data you got and try to make out the highest probability prediction out of this. So let's carry on. So there is fine-tuning and higher resolution aspects of this. These are technicalities of images, but I don't think they are essential for you unless you're super interested in this. You can dig deeper, but now you get the idea of even how the transformer architecture is doing in images. So if you thought, okay, I understood the transformer architecture, I wonder how images AI model work. Well, it's the transformer architecture. So let's move to the next one quickly. So this is a paper that came in 2022. I know Google got lots of heat in AI after ChatGPT, especially that they struggled a lot. I think they still struggle now, but also we cannot ignore the fact that lots of the things we have in our disposal today are influenced highly by Google. Such papers done by Google people who are clearly talented and experts in the domain. Here I want to talk about a concept called mixture of experts that they introduced, which is coming more and more. I hear the term more and more. So it's a modification to the transformer architecture. Again, works the same way. They just do things a little bit differently that I think you're going to hear this term a lot in the future. We will get into it when we go more deeper in shorter videos on a certain type of architectures or models or innovations. But I want just to quickly touch on that. I'll give you the link of all these papers if you want to do your... I read the whole thing before. You want to do your own digging. I think this is one of those kind of pivotal moments. So here, this is called switch transformers, scaling to trillion parameter models with simple and efficient sparsity. Again, still by that time, people were not talking about, hey, we can do so much better with smaller models if we do things differently. People were going for much bigger and bigger type of models. So the mixture of experts came here. And let's read this and just go off and look briefly of how that works, so you get the idea, and then we go to the next thing. So in deep learning, models typically reuse the same parameters for all inputs. Mixture of experts models defy this and instead select different parameters for each incoming example. The result is sparsely activated model with an outrageous number of parameters, but a constant computational cost. So computational cost is a big thing at that stage. However, despite several notable successes of mixture of experts, or MOE for short, widespread adoption has been hindered by complexity, communication cost, and training instability. We address these with the introduction of switch transformers. It was at that time mixture of experts they produced. It was a challenge. They had these issues, and then they solved it with switch transformers. We simplify the mixture of experts routing algorithm and design intuitive, improved models with reduced communication and computational costs. Our proposed training techniques mitigate the instabilities, and we show large sparse models may be trained for the first time with lower precision formats. We design models based off, okay, these are some of the standards, to obtain up to 7-time increases in pre-training speed with the same computational. So I think these are GPUs, T5 base. We design models based off, I'm not sure. Tell me in the comment section if you know. So where was I? 7 times increase in pre-training speed and the same computational resources. These improvements extend into multilingual settings where we measure gains over the MT5 base version across all 101 languages. I think these are like training data standards or databases maybe. Finally, we advance the current scale of language models by pre-training up to trillion parameter model. Okay, they're able to scale the number of parameters, work with much bigger parameters just by using the mixture of experts approach, which had issues, and they were able to solve that with the switch transformers. So let's quickly look at the introduction. Large-scale training has been an effective path towards flexible and powerful neural language models. Okay, simple architectures backed by generous computational budget, dataset size, and parameter count surpass more complicated algorithms. An approach followed by okay, so and so. While effective, it is also extremely computationally intensive. Inspired by those success of model scale but seeking greater computational efficiency, we instead propose sparsely activated expert model, the switch transformer. Okay, in our case, the sparsity comes from activating a subset of neural network weights for each incoming example. Okay, so what they're saying is, yes, what we found, and I think it was very clear that in GPT-3, OpenAI were hinting to this. The bigger the model, the more parameters, the performance increases a lot. OpenAI at GPT-3 had an accuracy of above 60% based on a 175 billion parameter model. Now they're talking about trillions at that stage of this paper, which was in 2022. So they say, yes, it works, but the problem is it's crazy computational requirements, it's crazy data requirements. We are suggesting something else, the mixture of expert and the switch transformer. And basically, rather than just going through one set of parameters altogether, we actually go to different groups of them, the way I understand it at the surface level of this thing. So let's go down and see what they say about here when it comes to the benefits of the switch transformer. Further, our large sparse models can be distilled, okay, into small dense versions while preventing 30% of the sparse model quality gain. Our contributions are the following. Forget about the above, maybe linked to the part above it. Now, I think this is like the contributions or the benefit. The switch transformer architecture, which simplifies and improves over mixture of experts. So apparently at that time, MOE was there. This is an improvement of it. This is the next step of it. Scaling properties and benchmark against the strongly tuned T5 model. So this is a model where we measure 7x pre-trained speed ups while still using the same flops per token. We further show the improvements hold even with limited computational resources using as few as 2 experts. So they broke down the whole model into two experts. They do the training using this approach of a switch transformer, and it's 7 times faster. Okay, let's continue. Successful distillation of sparse, pre-trained, and specialized fine-tuned models into small, dense models. Okay, the same concept they're talking about again. Improved pre-training and fine-tuning techniques. Selective, precise training that enables training with lower B-float 16 precision. An initialization scheme that allows for scaling to a larger number of experts. And then increased expert regulation that improves sparse model fine-tuning and multitask. Okay. They go around the same point again and again and again of how that works and bringing benefits in speed and computations, and how they still get that kind of a trillion parameter model benefits of that scale and size, but over these groups of experts or that switch transformer that we will read about here. So let me remove this to have it clear. Again, just super interesting. The guiding design principle of switch transformers is to maximize the parameter count of transformer model. See what they're referring to here? This is our original Attention is All You Need paper. So they still go to that. So you can imagine how much still relevant that video is to the models that we are dealing with even today. Okay, so you can read this at your own pace. The idea of this is best shown in this image. Let me read and then you can look at the image. So illustration of a switch transformer encoder block. We replace the dense feed-forward network. So the feed-forward network, which you can assume for a multi-billion parameter model, it gets a huge, so complex as a network and very heavy to train and deal with. So here they say we place the dense feed-forward network layer present in the transformer with a sparse of switch feed-forward layer, light blue. So this is the switch, basically part of it. The layer operates independently on the tokens in the sequence. We diagram 2 tokens, x1, which is more, and x2 parameters, okay, below. Okay. So this is based on 2 experts, somewhat you can say that, where the router independently routes each token. The switch feed-forward network layer returns the output of the selected feed-forward multilayer by the router gate value, dotted line. So what I understand, here you have 2 routers, and fundamentally each router will have multiple experts, and it will route that token coming in to that specific subset of a feed-forward network, and then it will carry on rather than going through the whole feed-forward network every time. Okay, that is the fundamental idea of that. So rather than dealing with these huge complex feed-forward networks, we actually break them down to experts. So I think this is how the correct understanding here. So we have 2 experts. Within each expert, you have a switch, and that switch will basically route that token to the subset of that feed-forward network. Correct me if I'm wrong. This is how I understand it. They call it here the switching feed-forward network layer. Okay, and I think we are still can use the concept of a mixture of experts here. So I don't know if these are 2 experts or just different ways to depict this. Anyways, so you can continue reading this one. The link will be shared again, but again, just to go to the first point before I jump off this one. Yeah, I think we're talking about experts, and within each experts, there's some routing happening. Do more reading there. I might do more reading on this one. I didn't read the whole one in detail, but definitely an interesting paper to understand. Okay, so let's jump on to the next one. So again, this is LLaMA 2 when it came out, and this is in 2023, July 2023. This is the LLaMA 2 paper that came out. We will definitely do a deep dive on, for example, LLaMA 3 or whatever comes out when I actually get to that paper. I wanted to show you a different approach that they introduced in LLaMA 2, and I think clearly after the last paper I show you, you will understand if I start covering more and more open source models in these kind of videos compared to closed source models. Okay, so here the one interesting thing, again, you can read through it. all of it till this moment, till 2023, heavily influenced by the transformer architecture. But I want to do this part here. So what LLaMA 2 did, again, all of these papers now get so interconnected that all of these ideas are not really new when LLaMA 2 bring them. So they're there, but I think one of the things, the way they did it differently, or they claim that it was kind of a big change in the performance compared to, at least when it comes to LLaMA's previous models, is how they structure the pre-training and the self-supervised learning. You can read about that. And then how it goes to the fine-tuning. And you can see it's here, supervised fine-tuning. There's exchange with the model. That exchange, again, you can imagine it as the window chatting with the model. Now, after chatting with that model, so that kind of conversation is happening, this goes back to a human feedback. So there's a human chatting with the model as they develop it, train it, or fine-tune it, and is giving the model feedback. So let's say they ask it, the boy went to the, and the model said, continue that for me. The model said school. They said, yeah, you got it right. It gave, for example, went to the cemetery. They said wrong, let's say. Just an example. So that human feedback is coming in, and what the model is doing as it is exchanging, it's fine-tuning. It is doing a rejection sampling and then proximal policy optimization. This is what they call the reinforced learning human feedback. So you can see the fine-tuning is happening based on reinforced learning through human feedback that is happening. So I will not claim that LLaMA is the one who brought this. Again, all of these concepts are already there, but definitely this is something that was significant for them. And even if you go to the top of the paper, again, I always say the first abstract and the introduction are always important, and I always also love to go to the conclusion. They say, we develop and release LLaMA 2, a collection of pre-trained and fine-tuned large language models ranging in scale from 7 billion to 70 billion parameters. We remember that I think everyone who worked with LLaMA knows these different parameter sizes of the model. Our fine-tuned large language models called LLaMA 2 Chat are optimized for dialogue use cases. Our models outperform open source chat models on most benchmarks we tested, and based on our human evaluations for helpfulness and safety, may be suitable substitutes for closed source models. So here they're beating on OpenAI, I think, and others who are closed source. We provide a detailed description of our approach and fine-tuning and safety improvements in LLaMA 2 Chat in order to enable the community to build on our work and contribute to the responsible development of large language models. I thought that part is important for you to see the architecture that I was just on. And they talk all about each step of this, how they do the self-supervised training, how they do the human reinforced learning and human feedback. You can read through it. The last paper I want to show is what we got in March of 2024. This is GPT-4. Now we're just way beyond that. We have 4.0, we have 0.1, I get it. And you can read this paper for yourself. And the reason before I said going forward, probably I'm going to be covering mostly open source papers unless OpenAI wants to share more. I'll just show you one simple and interesting statement in this paper that caught my eye when looking at this paper. And I thought maybe this is something the wider community or whoever is watching this wants to see for themselves. So here, scope and limitation of the technical report. So they call it a technical report. I think they're less revealing about what they do in OpenAI. We know that today, but this is in 2024 early. So here they talk about how they also use reinforcement learning and human feedback methods in their model. But this is the statement I want you to really look at. Given both the competitive landscape and the safety implication of large-scale models like GPT-4. So they're saying, oh, it's because of the competition, but also the safety. It's very dangerous to expose these things. This report contains no further details about architecture, including model size, hardware, training compute, dataset constructions, training method, or similar. They're telling you they're not going to tell you more about the architecture. And I think this will be the norm for companies with a closed source like OpenAI. And do with this piece of information what you will. So again, crazy long video, I assume as long as the previous one. If you watch both, if you actually have the brain cells, the attention span, you can do it actually over sessions, the heart and the stomach to go through these two videos. I think going forward, even if you skim through them, I think going forward, we can do definitely much shorter, like half an hour maximum videos where we focus on up-to-date, current happening type of studies and papers where we dissect even further what's happening out there. And I think with these two videos, the previous longer ones and the previous longer one about transformer architecture and this one, we have, I would say, 70 to 80% of the high level understanding of some of the concepts behind how these things work. You can see clearly while lots of methods are changing, the transformer architecture is still the one technology that is driving most of these things on both text and image, and I assume even video. Again, this is a video that I'm taking a risk on because it's long. If I mess up the thumbnail and the title, no one will watch it. It's out there for the ether to bring it to anyone who's looking for something like that. If you watched, thank you very much. If you actually watched it all the way through, write me a comment in the comment section. Let's see if this time someone actually does it. So don't cheat if you saw that part in the beginning only. Hopefully I earned your subscription. Maybe I earned a like and a share of this video. And maybe, just maybe, I earned a comment. Thank you for watching and goodbye.
Subscribe to Daddy's channel. Give me the mic.